Hey, welcome back to this short summary on electrical circuits and networks. So, in the last video, we discussed the solution to the second order differential equation. Uh, that was the LCR circuit, and based on that, we got what the natural response and the forced response to the solution are. And moving ahead with the same discussion, there is this lossless LC circuit that simply comprises of an inductor and a capacitor. That is the resonator, and its natural mode of oscillation is cos t by square root LC, 1 by square root LC being its resonant frequency, where it is interesting to see how energy gets transferred from the capacitor to the inductor and back again. And in the parallel and series combination of LCR circuits, we got two characteristic equations for the exponential response that we had guessed as its solution. So for the series combination, it was LCP square plus RCP plus 1 equals 0. And for parallel, it was LCP square plus L by R times P plus 1 equals 0. That is, the coefficient of P is different in both the cases. Now, to generalize this, we write it as p square by omega n square plus 2 zeta times p by omega n plus 1 equals 0. Both equations on careful observation can be seen to be of the same form, where zeta will decide the nature of the roots, because if zeta is 1, it will have equal roots, and the other cases. So what happens is we have to define some more terms here. So omega n is the natural frequency of the circuit. That is, in the both the cases, it is square 1 by square root LC. Q is the quality factor of the circuit. That is 1 by R square root L by C in the series case, and R times square root C by L in the parallel case. That is, it is the reciprocal of the series case. And zeta in the series case, it turns out to be R by 2 square root C by L, and parallel case 1 by 2 R square root L by C. So on having defined these terms, and now that we know the general equation, uh, general characteristic equation, where Z is the damping factor. Yes, Z is the damping factor. Uh, Now we can characterize the solutions as I discussed in the last video as well, that if Z is greater than 1, we will have real distinct roots. This is what we call the overdamped case. Now there is one more quantity that we can define, that is alpha, 1 by 2 RC for the parallel case, and similar for the series case as well, uh, just with a different uh, different value, just with different value. In parallel case, it turns out to be 1 by 2 RC, and in the distinct real roots case, alpha is greater than omega naught, that is greater than the natural frequency, and this is the overdamped case. Q turns out to be less than half. The second case which we saw was the equal roots case, where Z is 1 and Q is half. This is the critically damped case, where alpha is equal to omega naught. And the third case being the imaginary roots case, where Z is less than 1, Q is greater than half, alpha is less than omega naught. This is the underdamped case. Underdamped case being, if you remember, the decaying sinusoid was what we got as the solution. Okay, so alpha is also referred to as the Neper frequency and exponential damping coefficient in the textbook by William Head. And yeah, so this covers the classification of the solutions we obtained to the second order differential equation, and the last case being the undamped system or the ideal resonator, which we started the discussion with. That is, if Z equals 0 and Q tends to infinity, we get this ideal resonator, the LC oscillator. Okay, so now coming back from the natural response to the steady state response, or the forced response. Uh, as I said, if the input is an exponential signal, Vp exponential j omega t, in steady state, we can just find the values using 1 by j omega c and j omega l, or also we can say that uh, the output Vc of t will just be h of j omega times the input signal. So h of j omega being our transfer function, and on putting the equation back into the differential equation, we get the value for h of j omega, which turns out to be 1 by 1 minus omega square LC plus RC j omega for the series case, and the corresponding value for the parallel case. But when we write it in terms of omega, omega n, and q, we get same equations for series and parallel. That justifies the generalizing the substitution of by the zeta and omega n parameters has done. So uh, on having done this, we can observe the gain, that is the transfer function, that is plotting its magnitude and phase plots since it's a complex number. Coming to the Bode plots, here you can see that if q, the quality factor is 100, this is the kind of plot you would get for the magnitude, where omega is plotted on a log scale. And if q is managed such that it comes to be near about 1, uh, not very larger than 1, then this circuit can be used as a low pass filter. And on trying out various combinations of LCR and changing magnitudes of the parameters, we can of the components, we can observe different kind of filters, high pass filters, low pass filters, and again band pass, and so on. This is what the LCR circuit discussion, I think, concludes with. Uh, the Bode plots for angle and phase also can be seen here. Uh, Maybe that can be discussed in a different video. Uh, but I think this is how it sums up the solution for the second order system. Okay, thanks for watching, and let's see some power analysis in the next video. Hope this helps, and thank you.